How to find the direction of contact force, also called the normal reaction from a wall. So we are going to consider two situations. Case 1 will be a ladder resting on a wall. Case 2 will be a hinged ladder. By hinged, we mean the ladder is connected to a point about which it can rotate. So consider situation 1 where you can see the ladder is resting between the wall and a ground. Now let us identify the forces acting on the ladder. That is always the step 1. So in this case, the first force acting on the ladder, let us consider it to be the weight of the object mg acting downwards, and the weight always acts from the center of the ladder. Apart from mg, now since the ladder is in contact with the wall as well as the ground, it is going to experience a contact force, and direction of normal reaction is always perpendicular to the contact surface. So consider the ladder in touch with the wall. So normal reaction will be in this direction. So N1 is the normal reaction coming from the wall on the ladder. And the direction of N1, as you can see, is perpendicular to the wall. Similarly, the ladder is also resting on the ground. So the ground also will give a contact force on the ladder. Hence, now let us draw N2. N2 is the normal reaction on the ladder, but that is coming from the ground. And we can see the direction of normal reaction N2 is perpendicular to the ground. So the principle is very simple. Whenever the object is resting on a contact surface, the direction of normal reaction is always perpendicular to the contact surface. But if we take the same ladder and hinge it at a particular point, so consider this situation where the ladder is in this orientation, but let's say the ladder is fixed on the wall at this point. Now let us consider that the ladder is connected to a point on the wall, which is the hinge, which means the ladder can rotate about this point. And now, if we leave the ladder in this orientation, of course, because of gravity, it is going to fall down. But since the ladder is connected to a hinge, it is going to rotate in a clockwise direction. And in case of hinged objects, the normal reaction has been given a special name. It is called the hinge reaction. So, in all questions of rotational mechanics, whenever an object is connected to a hinge, the object is going to experience a force which is called the hinge reaction. And please read, direction of hinge reaction is not fixed. It always depends on the position of this ladder. So if we consider this orientation of the ladder, the direction of hinge reaction might go in this direction. On the other hand, let's say if the ladder is in the horizontal direction, then the direction of hinge reaction might be acting in this direction. Now, the actual direction of normal reaction is not important to label. And that is why I said direction of hinge reaction is not fixed, unlike the previous case where the direction of normal reaction is always perpendicular to the contact surface. The original case was the ladder just resting on the surface. Case 2 is the ladder being hinged at a point on the wall. Now, finding the exact direction of normal reaction is not very important for questions. But in questions, all we need to remember is the hinge reaction always acts on the ladder, but it needs to pass through the hinge point. So in both the situations, we can see that the hinge force N is acting through the hinge point. Now, why is that important? Because in the questions of rotational mechanics, of course, we need to find the torques, and torque is always supposed to be found about a particular point. Now, since the hinge force is actually a little difficult to find in questions, that is why to eliminate the effect of a hinge reaction, what we'll do, we will consider the point about which torques are to be found. That point is the hinge point. So let me repeat, we will consider hinge point as that point about which all torques are to be found, because if we do that, then we will eliminate the effect of the hinge reaction, because in that case the torque of the hinge force about the hinge reaction will be equal to zero. Because remember the principle, if the force passes through that point about which we are finding the torques, then the torque of that force about the point is considered as zero. And that is why I said to eliminate the effect of hinge forces or hinge reaction, we generally take the torques about the hinge point only. And let us try to solve a few questions first on the hinged ladder setup, and then we'll do one example where the ladder is just resting on the wall. So let's start with a question which is on hinged ladder. So here we have a uniform solid beam whose length is 2 meters and the weight is 800 newtons. The beam is in the horizontal direction as shown. It is hinged on the wall at the point A. The beam is supported by a string AB, which is attached to the beam at A and to the wall at B. Which of the following describes the magnitude of tension on the string? So, how do we approach such questions? Step number one is always to draw the free body diagram. So, consider this is the ladder which is horizontal. The first force is mg, the weight of the ladder acting downwards, and it is going to act from the center of the ladder. And mg value is already given in the question as 800 newtons. Then, the ladder is connected to a string, which means the ladder is going to experience a tension force. Remember, the direction of tension is always along the string and it is going to go away from the object. Hence, we can show the direction of tension acting in this direction, which is at 30 degrees to the horizontal, and magnitude of tension is T. Apart from these two forces, since the ladder is connected to a hinge, then the ladder is going to experience a hinge reaction, and we will show hinge reaction to be pointing in this direction. So, like I explained earlier, the exact direction of normal reaction is not very important because in most cases we are going to consider torques about the point O, then the torque of the hinge reaction will be zero. Now, coming to the main question, here the beam is supported by the string, which means the string is stationary. It is in equilibrium. Since the object is in equilibrium, we are going to consider the ladder in linear equilibrium as well as rotational equilibrium. After step one, which is drawing the free body diagram, step two is always the linear equilibrium. And in linear equilibrium, the net force acting on the ladder is zero, which means the total upward forces and total downward forces need to balance, and all the forces acting to the right and to the left, they need to balance. And how do we do that? So mg is acting along the y-axis, but n and t, they are neither along the x-axis nor the y-axis. So what will we do? We will break the n and t into two components. So let's say n has a vertical component ny, and the horizontal component of the hinge reaction, let's say it is nx. Similarly, for tension, let's say the vertical component is Ty and the horizontal component is Tx. Now, linear equilibrium, remember, forces need to balance. So, total upward forces and downward forces need to cancel out. Mg is the only downward force and Ny and Ty are the upward force. So, the equation should be Ny plus Ty should be equal to Mg. So, let's write down Ny plus Ty will be equal to Mg. This is our first equation. And then all the rightward forces and all the leftward forces need to balance. So nx and tx will be equal to each other. So let's write nx is equal to tx. Hence, we get two equations from linear equilibrium. Now, in the question, we are supposed to find the magnitude of tension. And how do we find T? Let's say somehow we are able to figure out Ty and Tx. Then we'll have to use the Pythagoras theorem, as in T will be equal to square root of Tx square plus Ty square. So we need to identify the value of Tx and Ty. This is where the problem will come because we have only two equations, but if you observe, we have four variables. So ny, nx, Ty, Tx. There are four variables but two equations, which means we cannot identify the exact values of these variables. And since we are unable to do that, we have to skip this particular step where we use the linear equilibrium. That is where we go to step number three, which is rotational equilibrium. And in rotational equilibrium, we know the net torque acting on the object should be zero, and we'll use the formula for torque is Rf sine theta. And of course, this expression will give us only the magnitude of the torque. Direction of torques we need to identify separately. Now, look at the free body diagram. We have three forces acting on the ladder, so we'll need to identify three torques. But remember, torque is always supposed to find about a particular point. So we need to establish that point. And like we discussed earlier, since we are dealing with hinge reaction, we will consider hinge point as that point about which torques are to be found. So in this question, we will find all torques about the hinge point O. We will start with the hinge reaction N. Since the hinge force is passing through the hinge point, the torque due to the hinge reaction will be equal to zero. Coming to mg, which is the weight of the object, the magnitude of mg is 800 newtons. So if I use the formula Rf sine theta, the value of F is mg, which is 800. And R stands for the distance between the point and the force. So if I draw a dotted line starting from the point O and going towards the force mg, so let's do that. Let's draw a dotted line from O and going towards mg. This is equal to R. R is the length, and the value of R will be half of the length of the beam. Since weight acts always at the center, so the length of this dotted line will be equal to half of the length. Length of the beam is 2 meters, which means the value of R in this case will be 1 meters. Hence, now let us write down the torque due to mg will be equal to 1, which is the value of R. F is weight, hence 800 newtons, and angle is 90 degrees. As you can see in the diagram, mg and R are actually perpendicular to each other. That is why we have considered angle to be 90. And if we solve this, we will get the torque due to mg as 800 Newton meter. Now, this is only the magnitude, but direction is also important. So if you look at the diagram, O is the hinge point. So mg, the weight, has a tendency to rotate the ladder in a clockwise direction. That is why the torque due to mg will be in a clockwise direction. And finally, we come to the last force T. T is the tension force. So the torque due to tension will again be Rf sine theta, where the value of F is T, which we are supposed to find. The angle theta is 30 degrees. R means the distance between the hinge point and the point about which tension is being applied. Hence, R is basically the distance between O and A, which is equal to 2 meters. So for torque due to tension, R value is equal to 2. And let's write down the torque expression for tension. That will be equal to 2 multiplied by T multiplied by sine 30, where 30 is the angle between OA and tension. And if we simplify this, we are going to get T as the torque due to tension. And if we observe the diagram, tension has a tendency to rotate the ladder in a anti-clockwise direction. That's why the torque due to tension will be anti-clockwise. Now, since the object is in rotational equilibrium, the net torque needs to be equal to 0. Hence, total clockwise and total anti-clockwise torques need to be equal to each other, like I have mentioned here. Torque due to mg is 800, torque due to tension is T. And if we equate, we'll get 800 is equal to T, and the answer we get is T is 800 newtons. If we look at all the options, option D will be the right answer for this question. So let's have a quick recap of how we have approached this question. Step number 1 is to always draw the free body diagram. And while drawing the free body diagram, do not forget hinge forces which act from the hinge point. That's the step 1. Step 2 in most questions is linear equilibrium, which means the net forces acting on the object should be 0. But when we did that for this situation, it was not helping us. It was not helping us get the value of tension which we required. That is why we skipped step 2 and directly jumped to step 3, which is rotational equilibrium. Now, whenever we are dealing with rotational equilibrium, we have to find torques. Now, torques are always supposed to be found about a particular point. And for questions where the objects are hinged, we always find torques about the hinge point only. And why do we do that? Because in that case, the torque of all hinge forces will be equal to 0. So effect of all hinge reactions can be discarded. And then we just balance the total clockwise and total anti-clockwise torques to get the eventual answer.